Good evening, everybody. Picking up where we left off today in class, we were talking about oxidation and reduction, what's being reduced and what's being oxidized. We were looking at these two elements, the metal and the nonmetal. And how the metal can give the electron to the nonmetal becomes reduced by gaining electrons, and the metal becomes oxidized by losing electrons. One of the things that we can use to help us remember this is something called Leo. Get my pen here. Leo, and then Ger, which is like Leo the lion. All right, so Leo means lose electrons, oxidized. Ger means gain electrons, reduce. It's a little mnemonic device to help with that. Another one that we can learn is oil rig. I think these are in your book in the margin somewhere. They talk about these. Oil rig is oxidation involves loss of electrons, reduction involves gain. So a couple of ways that you can go about trying to remember and put this into your mind for knowing whether something's oxidized or reduced. And then looking at when something is reduced, right here, down at the bottom it says it's the oxidizing agent. So it's kind of like they're opposites when you talk about what's being reduced and what agent it is. If it's reduced, it's the opposite, it's the oxidizing agent. And then if the species is oxidized, then the agent is opposite from that. It's the reducing agent. You caused something to be reduced. If you are reduced, you have caused something to be oxidized. So hopefully that'll help a little bit when it comes time to trying to remember these things here. All right, so what we're going to do here is just practice, if you will, what's happening with what's oxidized, what's reduced when we look at a balanced chemical equation. So in this particular equation here, this is our combustion of methane. Let's go ahead first of all and assign the oxidation states to each of the elements in this equation, and then we can figure out what substance has been reduced and what has been oxidized. Now, bear with me, it's about 9 o'clock at night. My brain shuts off at 8, so we'll see if I can get through this without too many mistakes. But when we look at the equation up here, let's look at the hydrogen. The hydrogen is typically a +1 oxidation state in its compounds, but there are 4 of them, so that gives us a total of +4. All right, and that means the carbon must be playing a -4 role. So we messed up already. Okay, the carbon is playing the -4 role here, so I'm going to put that over here for that carbon. Then we've got oxygen. It's in its elemental state, so its oxidation state will be 0. Over here on this compound here, the oxygen is going to be doing a -2 role, but there are 2 of them for a total of -4. We went over this in class today. And then the carbon then, since there's only 1 of them, to counterbalance this -4 here, the carbon must be a +4 in this compound. Over here in the water is the oxygen is a -2. There's only 1 of them. The hydrogen, as we said in its molecular compounds, is a +1, and you'll see that if we label that as a +1, because there are 2 hydrogen there, the total is a +2, which will then negate that -2 oxidation state of the oxygen, which will give us that neutral that we needed. We said we needed to have, that the sum of the oxidation states must equal the charge on that particular particle. So I know this looks kind of haphazard here, but let's change the color of my pen here and see if we can show you what's going on. So this carbon here is changing to, okay, that's not what I wanted it to do. This carbon here is changing from a -4 to a +4. So it's underwent a change. The hydrogen right here is a +1, and over on this side it's a +1, so the hydrogen didn't change its oxidation state. But you notice the oxygen here went from a 0 to a -2 in both of these compounds. So if I connect those two with another line, okay, then we see that the oxygen actually underwent a change. So the carbon went from a -4 to a +4. So it became more positive in its oxidation state, which means it lost electrons. Leo, Ger, lose electrons, oxidize. So the carbon here was oxidized in this particular reaction. The oxygen went from a 0 oxidation state to a -2 oxidation state in both of these compounds here. So the oxygen had a reduction in oxidation state, so it was reduced. So in this case, we've got the carbon is oxidized and the oxygen is reduced. Okay, and that'll be important later when we talk about our half reactions and having to divide a balance, or not even a balance, but a chemical equation into two half reactions when we need to balance with what we call half reaction method. And hopefully I'll have time to do that with you tonight. Okay, so moving on. I know the screen here will show all of those little numbers there in a much nicer form than what I did there. But so then what we've got down here, if you'll notice, they've split this reaction in half. They took the oxidized half, which was the methane here, the carbon, from that, and the carbon and the carbon dioxide that was oxidized. So they took those two species and they put them in its own half of a reaction. So CH4 going to CO2. It added, or again, it lost 8 electrons. You'll know that by going from a -4 to a +4, that would be a total of 8 electrons that are lost. So this one is our oxidized half of the reaction. And then they pulled out the oxygen and the two compounds the oxygen went to in this case, and they wrote another half reaction. And you'll see this O2, the CO2 and the water, and then this 8 electrons here is accounting for the 8 electrons that the oxygen gained in going through this process. Over here on this side, it started as a 0, and then this oxygen gained 2 electrons, but there are 2 oxygens in that compound, so it's a total of 4 electrons that were gained. This oxygen also gained 2 electrons. There are a total of 2 oxygens because of our coefficient here, so there's another 4 electrons that were gained. So in this actual reaction, this redox reaction, there were a total of 8 electrons that were transferred between the carbon and the oxygen. And so we've divided that equation into half. So we have the oxidized half and then our reduced half, and then it shows how many electrons were involved in that transfer. Now the thing I do want to emphasize here, this is just a bookkeeping tool. These are not ionic compounds that are transferring electrons from one thing to another and becoming charged in this particular case. Sometimes that is the case. The ionic compounds will have that happen. But when you have covalent compounds, we really are not making ions in these compounds. These are covalent compounds still. All these numbers are doing is helping us keep track of the number of electrons that are involved in the change that undergoes when this reaction takes place, and helps us especially when we're doing our balancing, as I said, that we'll see later on. So I hope that kind of makes sense to you. All right, so then here are our definitions again. Okay, oxidation is an increase in oxidation state or a loss of electrons, and that's where our Leo comes in. See if I can write with my mouse. That's really interesting, isn't it? Okay, there's our Leo. And then reduction is a decrease in oxidation state, and that would be our Ger. Okay, gain electrons, reduction. All right, so there we go. Hopefully that's a little nice acronym for you. And then the oil rig, some people really like the oil rig as well. So you just really have to work on memorizing those things. Okay, so in that case, we talked about carbon was the thing that was oxidized. Its oxidation state increased, the oxygen reduced, its oxidation state went down, and nothing happened to the hydrogen. The hydrogen just kind of didn't have any change take place. Now, when we identify what species is oxidized and reduced, notice up here it says the carbon is oxidized and the oxygen is reduced. That is true, but oftentimes when we report the answer of what was oxidized, you would maybe say the methane was oxidized and the oxygen was reduced. Sometimes you'll see, especially in your textbook, the answers in the back, they'll mention the entire compound that element is in, saying that was oxidized, even though really it truly is the carbon that was oxidized and the oxygen that was reduced. Okay, So looking at another reaction here, if we wanted to practice this, we saw this earlier in the lecture today. We said that sodium is a 0 oxidation state here. The chlorine is also a 0, right? But over on here, this side, we said the sodium was a +1 and the chlorine was a -1. So we can see now that sodium went from a 0 to a +1. So that is indicating an increase in the charge or the oxidation state. So that is a loss of electrons, which means the sodium was oxidized, and the chlorine became more negative. It gained electrons, so this is what was reduced. All right. So I hope that helps a little bit. Wipe that screen clean so you guys can see what's on there. All right. So sodium was oxidized, chlorine is reduced. Then you may have to use the terms oxidizing agent and reducing agent as well. So it's kind of an opposite effect here. So if you identify what species is oxidized, then in terms of what kind of agent it is, it's the opposite. It's a reducing agent. The chlorine is reduced, so it is the oxidizing agent. So they're opposites, if you will. Okay, so these are your definitions for your oxidizing agent, reducing agent. Now the AP exam, they say they're moving away from using the terms oxidizing agent and reducing agent. But again, when you get into college, your professors are going to want you to know about oxidizing agents and reducing agents, and so it's definitely worth taking the time to learn about those things. So you can read through that slide at your own leisure. All right, so what else do we have here? We've got naming again those substances, so I'm going to go through that real quick. All right, so we've got another example here of what's happening with oxidation and reduction here. I really like the yellow. Let's go back to yellow. Okay, hello, work for me, please. Yes, figures. That is not what I wanted. There we go. Okay, here we go. So aluminum is going to be 0 because it's in its elemental state. That will be its oxidation state. Iodine as well. Even though it's diatomic, it's in its elemental state. It's not bonded with anything, and there's no charge by it. Over here on our compound side, looking at this, you should recognize that that's an ionic compound with a metal and a nonmetal. So each of these ions are monatomic, which means they're going to their oxidation state will be whatever their charge is. Okay, so the iodine here is going to be a -1, and the aluminum will be a +3 in its oxidation state. So now if we want to identify what was oxidized, what was reduced, what's the reducing agent, what's the oxidizing agent, we see that aluminum went from a 0 to a +3. Its oxidation state become more positive. In order for that to happen, you have to lose electrons. That's oxidized. And the iodine went from 0 to -1 over here. So it must have gained electrons somehow, and that means that its oxidation state went down. So that's a reduction. Okay. Now, oxidizing agent, reducing agent, since aluminum is the thing that was oxidized, it is the reducing agent. Yes, okay. Keep. Oh, no. Okay, back. So reducing agent. Lost my pen. And then what was reduced is the oxidizing agent. So you'll have some homework practicing that. Okay. Let's see. I think that's enough for all of that. Just wanted to move all that so that you can, never mind. We'll just leave that on there. Okay, so moving on. Again, there's an example there. You can read through that at your own leisure. Here's a nice, pretty picture of what that is. We've got aluminum and iodine, and they're mixing them together and adding water, and you can see this nice little vapor that's emitted there from that. Okay, so here's another example. I'm not going to work through this. You can read through that at your own time. So I'm going to kind of scroll through that. Now let's talk about balancing redox reactions. It's really kind of the nuts and bolts of what I want to get to today, and I've got time. So most of this is found in chapter 18 at the end of your textbook. So I think the main part of what you need to focus on is around page 834, but you will want to definitely go back to chapter 18, and that's where we talk about balancing redox reactions using the half reaction method. Okay, now this is going to be pretty confusing at first, and we'll work a few examples, and hopefully you'll pick up on it, and then maybe on Friday we can talk briefly about it, answer any questions you have, and then you'll have hopefully plenty of practice. I look at it really as just like playing a game. Got to learn the rules of the game, and once you learn the rules of the game, you can just apply it to pretty much anything. All right, so I do want to read through these with you. So the first thing is we want to separate the equations. It's not going to be a balanced equation. It's going to be an unbalanced equation, and most commonly it will be a net ionic equation. So it might look kind of funny to you. You're going to have lots of positive and negatives in the equation and that kind of thing. But what we want to do is separate those equations into what we call half reactions, kind of like we saw before with the combustion reaction where we split it into the oxidized half and the reduced half. That's really what we're going to be doing here. So two halves that we're going to separate those into. And then once we do that, then we're going to go through a series of steps to try and balance that. Now step 2, you'll see here, is actually got quite a few different steps that belong with it. And we do need to do these in the order that they're given. So I'll just go through it real quick, and then we'll apply it to an example, and maybe it'll make more sense. So for each half reaction, you'll have 2 from step 1 above. We're going to first of all balance the elements that are in that half of reaction, except for hydrogen and oxygen. We're going to balance those later. First, we're going to balance the number of elements. So if you have 2 carbons on one side and 1 on another, then you need to balance that with coefficients, and we'll see examples in a minute. Then the next thing we're going to do is balance the oxygen. Now, how you balance the oxygen when we do the half reaction method is by using water. And you place water on the side of the arrow where you are deficient in oxygen. So you're trying to equal out the number of oxygens on both sides of the yield sign, and you're going to place water on the side that you're deficient on oxygen. However many waters to make both sides of the equation have the same number of oxygen. After you do that, you'll have added hydrogen as well. So your hydrogen is going to be in balance. So what we do to balance the hydrogen now is by adding the hydrogen ion. It's really important that you note that we're adding H plus to balance this. And again, you do it just like you do with the water. You're going to add hydrogen to the side of the yield sign where you're deficient on hydrogen. It doesn't matter whether it's in ion form or just in atomic form. You're just trying to balance the number of H's you have from the left to the right. You want it to be the same on both sides. Once you've done that, what will happen is your charge, if you look at all your little charges on all of your ions that you've got on one side to the other of the arrow of the yield sign, you're going to notice most likely that those charges, if you add up the charges on both sides, they're not going to balance. And what we want to do is we want to have the charges on both sides of the arrow match. We want, let's say we have a positive 2 on one side, we have a negative 1 on another side. We want those to both be the same, and we do that by adding electrons. So you'll write a little e with a negative as a superscript, and that little e will represent 1 electron. And what that electron will do is it will bring down those charges on whatever side has the higher number or the more positive charge. And once you go through these steps, you've done most of the work, but there's a little bit more that needs to be done, because in the end what we want to do is bring back together those 2 half reactions, and then we've got a little bit of adjusting we need to do, and we want to have a final balanced equation where all of the species, all of the elements balance, and the charges balance within that equation. So to do that, to bring those 2 half reactions together, we're going to move to step 3 here. And what we do is we need, before we can add those 2 half reactions back together, is we need to make sure the number of electrons match for both half reactions. Now, what do I mean by match? I mean that we have to have the same number of electrons in both half reactions. So what we'll do to adjust for that is we will multiply through whatever reaction we need to by some integer to make the number of electrons match for both half reactions. And those electrons will be on opposite sides of the arrow for both of those half reactions, because in the end, when we add those two half reactions together, we want the electrons to basically negate each other or cancel each other out. Again, I will show you examples of all of this so that you understand what's going on. Once we've made sure that the number of electrons match with both half reactions, we add the half reactions together. We're going to cancel out any identical species that occur on opposite sides of the yield sign. And that will basically be a simplification of the two half reactions. And then they will come together and they will make one whole equation again. And then we will double check that everything balances. We have the same number of elements, atoms, that is, on both sides of the yield sign, and that the charges balance from one side to another. A lot of times when you're done balancing half reactions, you don't necessarily have neutral species on both sides of the arrow. You may have some ions present, which is fine because we're oftentimes working with a net ionic equation, so spectator ions won't be present. But our goal is in the end to make sure that the charges balance or are equal from the left side of the arrow to the right side of the arrow. So hopefully that makes a little sense. Okay, now what I want to do here is I actually want to write this equation, and hopefully it'll work. So we've got MnO4 minus So there's our equation. So we've got this permanganate ion right here. We've got iron reacting together to form iron with a different charge and a manganese ion. Now this is not balanced because you go, wait, whoa, 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 what happened? We don't have any oxygen present anymore, and I've got all these charges. What the heck's going on, Mrs. Fairchild? This is our net ionic equation, and it is unbalanced. So what we're going to do is apply that half reaction method that we just went through and figure out how to balance this equation in the end so everything looks a little bit prettier. Maybe not writing wise, but at least with number of elements and charges. First thing we need to do is I want to assign oxidation states to all of these elements so you can see how we actually divide this up. There's an easier way to divide it up, but at first I want to go through this rigmarole with you. So let's identify what's being oxidized and what's being reduced. Remember, oxygen is a -2 oxidation state. There are 4 of them there for a total of -8. All right, the manganese has to counterbalance that, but we want the overall charge here to be a -1. So that means the manganese must be a +7. The iron is a monatomic ion, so this is its oxidation state. The iron over here is monatomic, so that's its oxidation state, as well as the manganese. Its oxidation state is going to be a +2 because those are all monatomic ions and they take their charge as their oxidation state. So what we'll see here is the manganese went from a +7 to a +2, which means that it must have gained electrons in order for its oxidation state to go down. So that means this part was reduced. Okay. And then the iron went from a +2 to a +3, so that means it must have lost electrons somehow, so it was the thing that was oxidized. So now looking at those 2 sets of arrows that I have here, we can pick out our half reactions. So the one half reaction is the MnO4 and the Mn2+. And the other half is this iron, the Fe2+ going to Fe3+. Those are our 2 half reactions. I could ask for questions, but you can't ask me because I can't hear you. All right, now I'm going to wipe out this bottom one here just for the time being so I can work on the manganese one. Actually, I might be okay with it. Okay, so if we go back, and you might be able to look in your book on page 834, that's where the steps are laid out if you want to have that open while you're looking at what I'm doing here. The first thing I'm going to do, I've divided into half reactions based on what's oxidized and what's reduced. That's the first step. Second step is now I want to balance each half reaction, so I'm going to start with this one. The first thing I check for is, are my elements other than hydrogen and oxygen balanced in terms of how many I have? I have one Mn here, I have one Mn here. So check mark, that is balanced. The second part of step 2 is balancing the oxygen. Well, I have 4 oxygen here. I have none on the right side. So what I'm going to do is I'm going to add in 4 water molecules. And what that does is that makes me have the same number of oxygen on both sides of the equation. But what that did is that changed my hydrogen. Now I brought in hydrogen that wasn't even present before. So what I've got to do is I've got to add hydrogen to the side I'm deficient hydrogen on, and that would be my right side here. And it's going to get kind of messy because I didn't leave room. I have 8 hydrogen here. I have none on this side, so I have to add in 8 hydrogen. So I'm going to kind of put that up here, plus 8 hydrogen. And we add in 8 hydrogen ions. That's really important when we use this method. So if we look at this now, it still looks like a mess, but if we balance, look and make sure our elements are balanced. 1 manganese, 1 manganese. 4 oxygen here, this 4 applies to the O back here, so I've got 4. I have 8 hydrogen here, and I just added in 8 hydrogen ions there. So as far as the number of atoms are in that respect, that's fine. What I've got to do now is balance the charge, and that's the 4th part of step number 2 that I was outlining for you before. This is where we look at the charge that's present on each side of the arrow. So over here, I'm going to add up all of these charges here. Keep in mind, this 8 gets distributed to this positive here. So I really have a plus 8 here, and I have a minus 1 here. So my charge on this side of my arrow is actually a plus 7. On this side, my water is neutral, so I'm not even going to add that. But I've got a plus 2 here, so this side is actually plus 2. All right, my charges don't match. I need these two numbers to be the same. They don't have to be 0, but they need to be the same. How do I fix that? I've got to add in electrons. So I add in electrons to the side that is the more positive side, because by adding electrons, you're going to reduce that side. So this is the side with the more positive charge. So I'm going to add in enough electrons to make my charges match from one side to another. So to do that, I'm going to add in a 5 electrons. So up here, this is really not, this should be linear, but I guess we're not going to be linear tonight. So there's my 5 electrons. If I add all of this up on this side, I've got 5 electrons here plus this negative charge. That makes a total of 6 negative. Got 8 positives, 8 plus, 6 negatives gives me a positive 2, and that matches with this side here. So actually, this is my balanced half, and that's my reduced half, so that's all balanced. Now if we go and look at our iron, the iron actually is a little simpler on this one because of the fact that all I've got is one element. I just have the Fe atom, or ions. So I don't need to, I count how many I've got. I've got 1 here, I've got 1 here, so I don't need to do anything there to fix that. The next thing is I need to balance oxygen. I don't have any oxygen, so I don't need to worry about adding water. Then do I have hydrogen that I need to balance? No, no hydrogen, so I don't have to add any hydrogen ions in. But I do have a discrepancy in my charges. This side is a positive 2, this side's a positive 3. I need to make those match each side. So I'm going to remember I'm going to add my electrons to the side that is more positive because it will bring down that charge on that side. So over here I'm going to add 1 electron. And in doing so, that makes this side a positive 2, which matches this side over here. Okay. So this half reaction, which is my oxidized half, is now balanced according to that half reaction method. I'm not done yet, though. We have to take these half reactions and add them together. And once I do that and I check that everything balances, I'm done. Before I can add them together, the big thing is I've got to check that this number of electrons here matches this number of electrons here. So I have 5 here and 1 here. Now, at this point, you can check yourselves. These electrons on the half reactions have to be on opposite sides of the arrow, because we eventually want those to eliminate each other and cancel each other out. And like species on opposite sides of the arrow will cancel out. So in order to get those to match, I'm going to have to take this equation here and multiply it by 5. So what I normally do is just put parentheses around it, and I put a 5 out there. Sometimes I rewrite. These particular equations take a lot of paper. Sorry guys, no Canvas on this stuff. All right, sorry. Chemistry is not very conducive to the computer stuff, although you will have computer chemistry classes where they force you to do it that way. All right, so now what I've done is I've just multiplied this. What that means is this reaction has to happen 5 times for every 1 time this reaction happens up here, so that the number of electrons are transferred completely. In this case, we do have ions involved, so we probably do have an actual transfer of electrons, unlike that previous example where I said we have covalent compounds and it's just a bookkeeping thing. It really is still a bookkeeping thing, but we do have ions involved here. All right, so this is my half reaction. This is my oxidized half reaction. Here's my reduced half reaction. Now what I'm going to do is I'm going to add those together. So what I'm going to do is wipe this screen clear, and I'm going to rewrite all this stuff here for you so that you can see what we had before. All right, so we had 5 electrons. Should have music playing in the background. Okay, there's the manganese half. The other half we had was the Fe, and we had a 5 here, didn't we? Oh, yucky plus sign. Okay, some things to note. There's my 2 half reactions. Hopefully I wrote everything down right. 5 electrons on the left side, 5 electrons on the right side. They have to match before you can add these 2 halves together. If they don't, you've done something wrong. If they're both on the same side of the arrow, you've done something wrong. Don't do this at midnight. It's the worst time to do half reaction methods because of all the little symbols that have to be carried down. All right, so I'm going to add these together. So here I'm going to draw my little line, and we're going to have a little plus sign. You don't have to worry about that. That might get confusing. If you are like species from the left to the right, you're going to cancel out. So those 2 things drop out. Then I look, okay, I've got 8 hydrogen ions here. I'm looking for that same species on the opposite side of the other half reaction. I don't have any other hydrogen ions here, so nothing can cancel out those. Permanganate here, there's no other permanganate here to cancel out, so there's nothing to reduce that. Let's look at the manganese here. There's no manganese on the left side of my half reaction down here. They don't cancel. And my water, there's no other water over here on this side to cancel. So essentially, I'm just going to carry everything else down. So let's show you how that'll look in the end. It doesn't matter what order you write these things in. Okay, I'm going to just do my, where's my phone? And then we've got, don't forget, we've got to bring down this guy, and this guy, because we're adding the 2 halves together. Okay, so there is my left side. Those are my reactants. My products, I'm going to bring down my Mn2+, plus my 4 water. And that takes care of those 2, but I also am bringing this down as well. So I've got to put plus 5 Fe3+. This right here is my result from all of that. It's a lot of work just to give you a silly, funny looking equation. What you want to do is once you've added these 2 halves together, you want to double check. Does everything balance? What that means is, do I have the same number of atoms of each element on both sides of the arrow, and do my charges match from the left to the right? So let's count. 8 hydrogen on this side, 8 hydrogen here, 1 manganese, 1 manganese, 4 oxygen, 4 oxygen, 5 iron, 5 iron. So my elements match. Now let's do charges. This gets a little trickier, especially when you're tired, so I hope I don't make a mistake. Okay, this 5 gets multiplied by this 2 because I've got 5 of these irons. So I actually have a positive 10 plus these 8, so that gives me a positive 18. Minus 1 gives me a positive 17. Gosh, I hope I did that right. Plus 17. Let's check this side. Is that right? Here we've got 5 times 3 is a plus 15, and another plus 2. This is 0. Okay, so that gives me a plus 17. Hallelujah, your teacher did it right. Okay, that's a check. Check, check, we're done. That equation is balanced. Now, hopefully it would look nicer than that when you're done with it, and I think I'll show you a screen that has one on there that you can see the whole thing. All right, so let's look at that. Whoa, bad. There we go. All right, so in this particular screen, just does it for you. I just wanted to work it step by step with you. They go through all of this stepwise, how to do all the different things. And then down here at the bottom, this, if you can see this right here, that is our result. That's our final answer there for that. And everything balances. So it's kind of cool. I like it. It's like playing a game. But that's how you balance half reactions, and we'll be using that throughout the year, especially when we get to electrochemistry, etc. Okay, I think I got time to work this one more for you, and then you guys are going to be sick of my voice. So here we go. I'll put this on another screen again, but here's our equation. They give you the nice words of what's going on up here. Again, it looks different. It's a net ionic equation. It is not balanced. The first thing we're going to do is assign oxidation states to everything to make sure that we can identify what the half reactions are. So I'm going to rewrite this on this next screen here. So we've got H. That's ethanol right there that I just wrote up there. That's the alcohol you can drink and not die. And then I'm going to put the last species right under here. I apologize for not having enough room and writing like a second grader. All right, oxidation states, +1 here. Oxygen are -2 for a total of -14. Okay. The total of the chromium and the oxygen oxidation states here have to add up to be a -2. So I know this needs to be a +12. So each chromium is actually a +6. Over here, okay, this one's a little bit more complicated just because there's more elements, but the hydrogen again are +1. The oxygen's a -2, but we actually have 6 hydrogen here, so that's a total of +6, right? We've got this -2 here, so that brings it down to a +4 for this grouping here. I hope you followed that. That means the carbon must be a +4 because this whole molecule here is neutral. However, we have 2 carbon that this +4 must be distributed to, so this carbon here, each carbon here is actually a +2 oxidation state. So, yeah. Okay? Did I do that right? No, you know what? I added this wrong. This should be a +4. All right, and this here should be a -4. Sorry, you guys. I wonder if I can get that fixed there. Not that. Okay. It's going to be -4, so this should be a -2 up here. All right, there. Sorry about that. So we have a -2 for those carbons there. Chromium is going to be +3 because that's a monatomic ion. The carbon dioxide, we're going to -2 for that oxygen, but there's 2 of them there, which is a -4 total, so this carbon is a +4. The water, that oxygen is a -2, and this hydrogen here is a +1 for each one of those. Okay, so I went through the last part kind of quickly, but hopefully you followed that. Okay, hydrogen, +1 here, +1 here, and over here it's still +1. So the hydrogen did nothing, did not change. The chromium here is a +6. The chromium over here is a +3, so it changed. It went from a +6 to a +3, which means its oxidation state went down. So the chromium reduced. All right, let's see what else. The oxygen's -2s all around, so it didn't change at all. Let's take a look at this carbon. Carbon, this is a -2, remember. So we've got a -2 here, and it went to a +4, so it became more positive. So I'm going to have an arrow going over here to this carbon, and that became more positive, which means it lost electrons and it was oxidized. So now if we follow those messy arrows there, we can find our half reactions. Nothing really happened with the water, the hydrogen here, nothing really happened. So our two half reactions, which I'll rewrite in a minute, are going to be Cr2O7, 2-, and then the other component of that is its pair over here, which is the chromium. Okay, that's one half reaction. The other half reaction is this ethanol here, C2H5OH, and it reduced down in this carbon dioxide here to CO2, and that was oxidized. So those are my two half reactions. You say, well, what happened to this hydrogen ion? What happened to this water here? What you'll see, I'm going to leave those out. And the reason I'm going to leave those out is because when we go through our steps for balancing our half reactions, the water's going to come back in when we go through our steps, and so is the hydrogen ions. They're going to come back in. So I'm leaving those out right now. Nothing really happened with them in their oxidation states anyway. So here are our two half reactions we're going to work with. So I'm going to clear the slide again, and then we're going to start working on balancing those two half reactions. I'm going to do this without messing up again. Okay, so I'm going to work with that chromate one first, Cr2O7. Let's just do that one, okay? All right, so this one was the one that was reduced. We're going to go through the steps of our half reaction method. First thing is look at the elements other than oxygen and hydrogen. Chromium is the one we're going to look at. We have two chromium here. We only have one on this side. So we're going to add, just like we did when we do our other balancing, what I call our original balancing, our old-fashioned balancing, I'm going to 2 in front of that. So now I have the same number of chromium on each side. The other thing I need to do is I need to add balance my oxygen. 7 on this side, none on this side. So I'm going to add water to the side I'm deficient on oxygen. But I need to add the number of water as I have oxygen that I'm deficient by. So I really need a 7 in front of that water. Now when I do that, I've added in this hydrogen here that's not present on the left side. So I'm going to add in hydrogen ions now as the species to balance these additional hydrogens I placed here. So on this side, I'm going to add, well, let's see how many hydrogen. I've got 7 water molecules, 2 hydrogens in each one, so that's actually 14 hydrogen ions I'm going to add in there. And that's where you stop with adding in elements. Let's count again. Chromium, we have 2 chromium. 7 oxygen, and I got that 7, looks like a fish hook, times that O, so 7 there. And I have 14 hydrogen, and this messy stuff over here is actually 14 hydrogen. So I'm balanced in terms of my atoms. Next thing I do is my charges. Okay, so I have a positive 14 here, and 2- here, which is a total of +12 on that side. Over here, the water is neutral. I have 2 chromium ions that are 3+, so the total on this side is a +6. They don't match. I need these numbers to match. How do I make a match? Then I add in electrons. When you add in electrons, it's going to reduce the side you add them on. So you want to add it to the side that's the more positive side, which is over here. So I need to add in a total of 6 electrons to bring this down to match that 6 over there. So over here, I'm sorry, if I had more space over here, I would be adding in +6 electrons. And that takes care of that half. That one's done. Boom. The other half we had was the ethanol. We had C2. Okay, that was the other half we had. Elements first. Carbon. 2 carbons here, 1 here, and I put a 2 right here. Now I do oxygens, the next element. I have 1 here, I have 4 here. So I need to add water, and I need to add it to the left side, and I'm going to add 3 water. A little plus sign in the middle there between those. Okay, hydrogen's done. Now let's look at our oxygen is done. Now we're looking at the hydrogen. I have none on this side. I have 6 from here, plus 5, plus 1. So that's 12 hydrogen I have on that side. The right side, I'm going to add in 12 hydrogen ions. Elements should be balanced. You can always go back and double check, but I'm pretty sure that's okay. Now what I've got to do is balance my charges. So on this side here, this is deceiving. This is just a plus sign separating these two species, 0 and 0. So I have a 0 charge on this side. Over here I have 0 and I've got plus 12. All right, so that means that I need to add electrons. I'm going to add electrons to this side so that the charge on this side balances the charge on this side. In this case, it's 0, so I want to bring this side down to 0. And I'm going to get rid of this here. So it's not so bad. Okay, so there's our 2 half reactions. Now I need to add them together. Okay, I'm going to rewrite this up here, so let me clear this whole slide. Let me do that while you guys, I'm going to pause. All right, so I rewrote those 2 half reactions so we can add those together. So let's add, okay, I didn't want that. Sorry, everybody. Add those together. The problem is I have 12 electrons here and I've got 6 electrons here, so they need to match. This is where I'm going to take this whole half reaction, multiply the entire thing by 2. So that's going to make this 12 electrons, 28 hydrogen, 2 dichromate, 4 chromium, and 14 water. And I'm going to add all of that together. I'm going to cancel out like species from left to right. Okay, if I have the same species on the left side, it's going to cancel out with the species that are on the right side that are exactly the same. So essentially I have 12 electrons here, I have 12 electrons here. So those electrons are going to wipe out. I have 28 hydrogen. I've got 12 over here. So I'm going to lose all of these hydrogen are going to go away. And 28 minus 12 is going to give us, what, 16? And so we're going to end up on this side with 16 hydrogen ions. Okay, and then those species will be taken care of. Chromate from the left to the right, I only have this. Okay, so I'm going to bring that down. Then what other do I have? I've got, these are my other reactants I need to put down. So I've got 3 water here. I have actually, remember, 2 times this 7, so I have 14 water on this side. So all of these are going to cancel out. And then 14 minus these 3 is going to give me 11. And that'll be actually on the product side. So I'll do that in just a second. And then the ethanol here, I don't have anything to cancel with the ethanol, so that'll sit there, the reactant side. Okay, that should take care of it. Hydrogen, chromate, water is canceled in the ethanol. Okay, so then on the product side, I'm going to have these 2 chromium. There's nothing over here on this equation to balance or to counteract that. So that's Cr2 plus. We just talked about the water. These 3 go away. My 14 gives me 11 remaining. And then the other product I've got is this guy right here, my carbon dioxide, so I can't forget him. So I'm going to write 2CO2. Then when I'm done, this is my equation, and hopefully it's balanced. We check. 16 hydrogen plus another 6 is 22. Do I have 22 on this side? What did I mess up? Yep, I got 22. 11 times 2 is 22. Chromium, I have 2 chromium here. I got 2 chromium here. Oxygen, 7 here, plus this one is 8. Here I've got, is that right? 7 and 8. Oh, that's not working. Did something weird. Hang on. Okay, found it. Sorry, you guys. Made a mistake. Easy to do. Great example for you all to see. This 2 needs to be multiplied by my dichromate here, so I really need a 2. Okay, where are you? I need a 2 in front of this. Make sure I got my pen. Okay. I need a 2 in front of that dichromate, and that means this is actually a 4 chromium. And I distribute this 2 up here to the chromate, and then this 2 to the chromium here. So that was my mistake that I didn't catch earlier. You guys probably caught it. So let's recount. 4 chromium, 4 chromium. We're still okay, but let's go back to our oxygen. I have 2 times 7, which is 14, plus this one here is 15, and then when we go down here, we look at, we've got 11 oxygen, plus these 4 here, so that gives me my 15 that I was missing earlier. Carbon, 2 here, 2 here, and I think we already did our hydrogen, so everything should be good to go. The next thing we look at is our charges. I've got 16 positives and 4 negatives. This 2 gets distributed, so that gives me a plus 12. And then over on this side, let's pray that that works out okay. I've got, what did I do? 4 times 2 is 8. That doesn't match. Again, what did I miss here? Something. Hang on. Okay, again, it's late. This is my mistake right here. This should be a 3. This must be a 3 plus. Okay, if I can get it to go. Why are you not writing for me? This should be a 3. Not you. Okay. This should be a 3 plus right here on this chromium here. That's where my 12 is. So 4 times this 3 plus gives me a plus 12 on this side. So my water's neutral, my carbon dioxide is neutral. So in the end, this is my result right here. Let me draw with my finger. It's my balanced equation. Of course, it would need to be rewritten in a much nicer format. But in essence, that's half reaction methods. So hopefully you get the gist of it. We'll kind of answer your questions that you have on Friday about this. There is an extra step that we need to talk about when we have basic reactions versus acidic reactions. So we'll discuss that as well. But hopefully this was somewhat helpful to you. And again, you feel free to look through the rest of that part on the slideshow that covers that. Might give you more specifics, and obviously we'll not have all the little mistakes in there. So take a look at that. I'm going to post your homework on Canvas for what you need to try and work on, and we'll go over that on Friday. Give it your best shot, you guys. Good luck. Have a good Thursday night.